So remember, we talked about the 2D distributed load, that if you have a beam, for example, and there's a distributed load on that. Kind of distributed. For example, let's make it simple. I have the simple distributed load like that. Yet remember, when it says that what we need to do is that we have to replace that with a single load. So we can work with that. We cannot work with a distributed load like this in just a 2D condition. So it was 2D. And we said that we are going to replace that load with a single load that goes through the centroid of the area of the load. So, for example, this is a rectangle. You know the centroid of that is here. So that load will pass through that centroid of that load. And the amount of that load, the magnitude of that load, was the area under the curve. So if I go ahead and say, okay, this is the R, and this position is going through, as soon as it's going to be the X. So the X would be entire things here. X would be the X of the centroid for the load. X, so centroid for the load, the X for the centroid, which for the rectangle would be half of the total X. Then, so it will be located at the centroid of the load. And then we had the magnitude of that. So that's where it's located, and its magnitude was the area, was W times L. Or basically, it was with the area of the load. Okay? So now we want to see what would happen if this is going to be in 3D. So instead of having it in 2D, it's very similar to that. First, I want to start with this simple case. So assume I have a plate that it has a no uniform distributed load on it. So I'm having a uniform distributed load there. So I need to replace this entire load with a single load like this, called it the FR. And the distance for that is going to be the X in this direction and Y in that direction. So if it is in 3D, doesn't matter the shape, the location, the X and Y, are the center of the volume. So they're located So wherever is this center of volume for the load, that force will be passed through it. Right here, find the center of the area and say, okay, the resultant force passed through it. Here we will find the centroid of the volume, or the center of the volume, and say that's going to be passing through. The magnitude of that, the Fr. Here the Fr was the area of the load. Here is going to be the volume of the load. So whatever is that volume, that's going to be the Fr. So it's going to be volume of the load. So for example, if I go ahead and say this is W Newton per square meter, this time is per square meter, and then I'll go and say so it's going to be the L, and this is going to be the say, H. Then the Fr would be W times L times H. That's going to be the volume. But where is that volume? That assumes a uniform.
So our square is basically our rectangle at the moment looks like it's 2D. So the volume is the volume of the force. So like H would just be how tall it is, basically, like how tall the Z-axis.
No, I didn't want to use the W because is the X, Y, and W is the Z.
Yeah. Okay.
If you know any other letter than H.
Well, oh yeah, I misread my own handwriting. So that's
So the area of the base basically times the
yeah.
times the W.
Yeah, I misread my own handwriting.
Again, one thing is that, and this is gonna help you a lot in fluid mechanics when you take it. Usually, the fluid or any pressure is 3D. Fluid mechanics or any pressure vector. And it's not that easy to work with the 3D distributed load. So one way that most likely you are going to end up doing that is you convert the 3D load to 2D load, and then you convert that 2D load to the single load. It's usually easier to work with that rather than try to convert from 3D directly to a single load. So, what is that if I want to convert 3D to 2D? Or 3D to 2D. So, how will we do it? So, assume again I have the same area, same base. And make it E, so maybe it's easier if I make that E. That's confusing. Assume I have that. And then I have a load on these. That looks like, example like this, I suppose, like here, So at this end, it's going to be W1. At this end, it's going to be W2. So it's going to be W1. It's going to be W2. So it's changing in the length over the length. So it's changing through the length, but assume it is not changing through the width. Okay, so it's constant through the width. If I go through the width, it's constant. Through the length, it's changing. Okay, so if it is like that, I can go and compress it like this. Bring the entire things to that front edge. Because it doesn't change in that direction. So I can go ahead and say, I will bring the entire, so I will draw this, if this is the AB, I will draw the AB, and I will put the new load on that. So, and this becomes W2 times P, this one becomes W1 times P. And then I have the rest. So I will go from this to this. If there is no change, in the load line B direction. So if change along B doesn't change, I bring the entire volume. So basically, I bring the entire volume to that front edge. I put it on the front, compress it and put it on the front edge. And then from here, whatever we learn to do with the 2D, we can just do it from. Okay? And remember that these are Newton per square meter. These are become Newton per square, Newton per meter. But I just multiply them by the length. So from the pressure format of the 3D distributed load to the 2D. And usually in fluid mechanics, if you're given a 3D object, try to do this, try to bring it from 3D to 2D, and then that's what we did so far, and do it right here, like that. Good question. very briefly about the fluid pressure. So, for the fluid pressure 2D, I have the water level there, and there's going to be an object sitting down there, like that. The pressure at any given point would be P is equal rho G. It was rho Gh, but the rho Gz. And in this case, we can write the coordinate axis would be, this is going to be the x, and this is going to be the z. So z is 0 at the surface and increasing, going down. Rho is the density of water. Density, and z is depth, or distance from the surface. Remember that we start at 0 at the water surface, and it's going to be positive as long as we go down. So the positive downward. One other point that I want you to make sure that the pressure, there are two properties. It's always toward the object, always perpendicular to the surface. Pressure always toward the object, always perpendicular to the surface. So if I have it here, so it's going to be all perpendicular and toward that. And the more I go down, it becomes larger. So, the 2 points. Pressure is always toward the surface or toward the object, whatever surface you have. And pressure is always normal to the surface of the object. So, always toward it, always perpendicular to the surface at any point. So, if you're asked to do that, you can write. Just 3 quick example. So, about the z, that one can find the z and the one. So the first one is that if this is a water surface, and there's a point P here. That is going to be the z, correct? Normal distance from the surface to that point. Now if I have a container look like this, at the same point here. Water surface. Where will be the Z?
Still be in the same spot.
So the Z is still is going to be, it doesn't matter how much water is on top of that. Still the Z is going to be from the water surface. Another example, if I have a container like this, then I look at the point somewhere here. The Z would be
From the surface.
Z would be again from water surface. That's the Z. So the depth is always from the water surface. It doesn't matter how much water is on top of that point. You don't care about that. You have to go and see and seek this free surface and directly go down from there. That's the value of this. Any question? So we're going to chapter 10. Chapter 10 talk about the moment of inertia as if it is not the most important chapter in the entire statics, one of the most important chapters in statics, because this idea of that we have here, we are going to use it in many design courses that in mostly solid, but even in the fluid. It's very important topics to work with that. You have to know how to work with that. So, okay, start with a simple example. Um, so I have like this. And so it's sitting on some kind of support. And then assume I have another beam. So this one is sitting on some kind of support. So that's the case one, the case two. So if I go ahead and put force F right in the center of that, that beam is going to deform, it's going to deflect and go down, correct? So now, if I go ahead and put the same amount of force here, whatever force I have there, I'm going to put the same right there. So it's the same beam. I just once put it like this and then like this. For example, if you look at this ruler, once the first one is looking like this, and I put some force on that. The second one I put it like this. The same thing. Which one bend more? So it's the same thing. Why this one bend more? It's what?
Yeah, it's smaller,
So physically. So so you know that by experience that this one will be bent more. So if this one, for example, comes like this one's will go down very, very, very tiny. Compared to that one being much more than this one. So the reality is that if I look at them from the cross section and go there, which axis is going to bend about it? The axis that passed through here. So I call that A. So it's gonna, so if I draw it from the front, that's the force on that. F. And it is bending about that A. Now, if you draw the same thing here, the axis that is going to be, this one is going to be bent about it is the axis that's going to be that. A again. So that's going to be the A. And it's going to be F. So I agree up to here. So just say this is thinner than that one, that's the thicker one. What the other way you can put it? Because they have the same area, same amount of material, same type of material. Correct? If I want to put it another way, why this one bend less than that one?
Is that one have more inertia?
Has more what?
Inertia?
So we get to there, but before that.
It's
got more weight.
Getting close. So it's the same material, just different arrangement. Here, look at here. How is the distance of the material from the center? From the axis that what you're bending about. It's very small. Here, I put the material further away from that axis. The further I move the material about that bending axis, the harder it's bending. And that's the concept of moment of inertia. So basically it says how hard it is to bend something. So two things. The further away cross section material from bending axis, the harder to bend. And the larger amount of inertia, again the harder bend. So you probably seen that most of the time the beam that they use to build the building has a very specific cross shape. They have the I cross shape. you saw that most of the beam they are using to build the building, they have the cross shape like this. Sometimes the three pieces of wood, that one of the horizontal, one of the vertical, and one of the horizontal underneath. That's a cross section. And that's exactly why they put it like that. We want to move away the material, the cross-section material from the bending axis. So the more I move this material away from the bending axis, that beam can withstand more load. It bends less. So that's why they make the beam with the I cross-section shape. So any question about the concept of moment of inertia? Before I go and say like actually how we can calculate. Similar to the centroid, when we wanted to calculate the centroid, remember we started with the general shape that we calculated by integration and find the centroid, and then we move on to known shape. If there are known shape, how we can find the centroid. It's the very same thing we do it for the moment of inertia. First we started with the general shape as if some shape that we don't know how we can calculate the moment of inertia. And then we will move on to, because mostly when you are designing with the geometrical shape that you are familiar with, not just some random shape. So we'll see how we can calculate moment of inertia for that. So assume I have x, y. I have some kind type of shape like this. So that is my cross section. Okay, so if I have a beam, for example, like that, if that was my beam, that's its cross section. So assume I have a beam that has a cross section like that. That's the cross section of it. So this is cross section. There you go. Now if I go ahead again, because it's going to be this form of integral, I go ahead and assume I get dA. That is dA. And that dA, the 3 coordinate, it has an x, it has a y, and it has r. If this is the case, the moment of inertia about x-axis, so the I about x-axis is the integration of y squared dA. The moment of inertia about y-axis is going to be x squared dA. And then the moment of inertia about O, that's going to be the O. The moment of inertia about O usually should be J. It's going to be R squared dA, which is going to be x squared plus y, which is going to be basically 5x plus y. So the unit for them next to the power of 4. The unit of them is a meter to the power of 4, or foot, or whatever. Another thing is that Ix and Iy and Jo, all of them is always positive or 0.
That cat just is not enjoying today.
Doesn't want to cooperate. So it's always because the x, y, and y is x and y and r, or r to the power of 2, so they're always positive. One thing about them is that they are usually a very, very big number, because it goes eventually to the power of 4, you end up with a very large number. Here's the point. When we want to do the centroid, I said we will use the dA either parallel to the x or parallel to the y, and we do all the calculation. Correct? Here we don't do that. Here we choose the element parallel to the axis that we want to calculate about it. So if I want to calculate I about x, my element should be parallel to the x. If I want to calculate I about y, my element should be. So this time I have to choose 2 different elements. In the centroid, I could have done it both with one element. Here I can't. Here I have to have 2 separate elements. So that's the point that choose dA parallel to the axis that we want to find moment of inertia about that. So if I want to find moment of inertia about x, my dA should be parallel to the x. If I want to find the moment of inertia about y, my dA should be parallel to the y. That's very important. Got it? Okay. So let's go again and assume I have the same. So if I go ahead and say, okay, this is the x and y axis. Then I have same cross section area. Cross section A. And that cross section is going to have a centroid somewhere here. X prime, y prime. So x prime and y prime are the axis passes through the centroid. So if this is the centroid, the x prime and y prime are the axis that are passing through the centroid. You clear up here? So, and then there's a distance between these two, so it's going to be, this distance is going to be d sub y. And remember, this is d sub y. This distance is d sub x. And the distance between O and there is got just simple d. In that case, the Ix is I about x prime plus, and usually they put bar on top of that, plus a d sub y squared. I about y is I about y prime plus a d sub x squared. And j about O is j about c plus a d squared. So one thing I want to make sure that you remember, don't get confused. So d sub y is d sub x is not dx, and d sub y is not dy. Make sure you don't get these two don't get confused. D sub x and d sub y are distances. Okay? So the distances, these two are distance. These two are differential element. So these are just distance. So why this is very important, and you're going to use it a lot. And why it's important? The reason is that generally most of the shape that we have, we know the I about the axis passed through the centroid. Usually we are given that. There are at the back of the book here. If you look at it, the I for the axis passes through the centroid are given. So the I about x prime or y prime are given, that's known. And usually, instead of it going there and do those integration, we just simply, because these two are known, the distance between that x prime and x is usually easy to find. The area is easy to find, so we can use this equation rather than doing that entire integration. So that's why it makes it much easier to calculate. And you'll see that when we do the example, we try as much as possible to use this equation to find the, for example, the moment about the x, rather than going there and solve that integral. It just makes it much easier. Question?